this is the solution to number 49 from homework 4.2, day 1. We're going to analyze and graph a rational function. In this case, we've got the rational function x cubed over x squared minus 1. We're going to begin by factoring the numerator and the denominator. The numerator is factored. The denominator is the difference of squares, x squared minus 1, which factors as x plus 1 times x minus 1. To find the x-intercept, we're looking for values that make the numerator 0, but the denominator cannot be 0. In this case, x cubed is 0 when x is 0, so we have an x-intercept at 0, 0, and that has odd multiplicity because the exponent here is a 3. Right? We have x cubed. Y-intercept, we're going to find f of 0. F of 0 in this case is 0 over negative 1, which is 0. So we have a y-intercept at 0, 0. Vertical asymptotes, we're looking for places, x values that make the denominator 0, but we have to make sure that the numerator is also not 0, because then we might have a hole. In this case, the denominator is 0, x plus 1 is 0 when x equals negative 1, and x minus 0 is 0 when x equals positive 1. We don't have a common factor, so we don't have to worry about holes here. Each of these vertical asymptotes has odd multiplicity because the factors that give rise to these zeros only occur one time. The infinite asymptote, we're going to look at the degree of the numerator and the denominator. Here, the degree of the numerator is 3. The denominator is 2. So this function is top-heavy. So it does not have a horizontal asymptote. But since the degree of the numerator is exactly one more than the degree of the denominator, we do have a slant asymptote. Right? We have a slant asymptote because the degree of the numerator is one more than the degree of the denominator. That's how we know we have a slant asymptote. To actually find the slant asymptote, in this problem, I'm going to do long division. You could do synthetic division twice with each of these linear factors, x plus 1 and x minus 1. I'm going to do the long division here, so I'll do that over here. So we're going to divide x cubed, and I have to put placeholders in for the missing x squared, x, and constant term. I'm going to divide that by x squared minus 1. So I say how many times does x squared go into x cubed? That's x times. Then I multiply x times x squared minus 1, which gives me x cubed minus x. Then I subtract. So x cubed minus x cubed is 0x cubed. So I'm going to have 0x squared. 0x minus negative x is going to become a positive x, so plus x plus 0. And then how many times does x squared go into x? It doesn't. So my slant asymptote is the quotient, which is this x term. So my slant asymptote here is actually the line y equals x. We can ignore the remainder when thinking about the slant asymptote. Okay, so this is our slant asymptote. And then we want to know, does this graph intersect the line y equals x? It's infinite asymptote. To do that, we'll let the equation for the infinite asymptote equal our function. So when I multiply both sides by x squared minus 1, I got x squared minus 1 here. I'm going to get x cubed minus x equals x cubed. X cubed minus x is never going to, well, actually, one is this going to happen. I can subtract the x cubed, so I'm going to get negative x equals 0 or x equals 0. So the only place that it intersects is at x is 0. When x is 0, if I want to know the y value, I can look at the slant asymptote. So when x is 0, y is also 0. So it intersects at 0, 0. Okay, let's put these pieces onto our graph. So the x-intercept is at 0, 0. It has odd multiplicity. And then I'm going to put on my two vertical asymptotes. I'll put a little O there. My vertical asymptotes are at x equals 1, which is odd, and x equals -1, which is also odd. And this x-intercept's odd. I'm not going to put the little O there because I guess I can put it here. It kind of gets in the way. And what else do we know? We have an infinite asymptote at y equals x. So we're going to go ahead and plot the line y equals x, which has a y-intercept of 0, 0 and a slope of 1. So that is our slant asymptote. And now we need to sketch the rest of the graph. So we know that the function is going to have to cross the x-axis at 0, 0, but it's unclear which way it's crossing. So let's get one additional point to help us. Let's get an easy point. So I'm going to get f of 2, because sometimes you do need an additional point in order to graph these. So f of 2 is going to be 2 cubed over 2 squared minus 1, which will be 8 over 3. So I know the point 2, 8/3 is on our graph. So I think that should help be enough for us to graph. So I'm going to put 2, 8/3. 8/3 is 2 2/3. So somewhere about that. And from that, I think we know enough to sketch a graph, because now I know that I need to approach the vertical asymptote at x equals 1, and then the slant asymptote as x goes to positive infinity. So that takes care of that branch. When we go left of the vertical asymptote at x equals 1, this vertical asymptote has odd multiplicity, which means if it's going, the graph is going up on the right side of the vertical asymptote at x equals 1, it's going to be going down on the left side. Then we know our graph is going to have to cross through the x-axis at 0, 0, and then approach the other vertical asymptote at x equals -1. When we go to the negative side of -1, so to the left of -1, remember this was an odd vertical asymptote. That means if the graph was going up on the right side of x equals -1, it's going to be going downwards on the left side. So I'm going to sketch that. And then I know that as x goes to -infinity, it has to approach the slant asymptote.